Okay, I think we are already a little bit delayed, so please find your seats. Why is it always like this? When you say 15 minutes, it tends to be like 20 minutes, something. Huh? Please come in, quick. There will be breaks later also. So take your seats, and I hope that now you will enjoy looking into the storage area of three projects. And we will start off with the SENSE project, also a very interesting name of a project. The ground surface monitoring, Barman. Welcome.
Yeah, thank you, Ragnhild, for presentation. Yeah, my name is Bahman Bohluli, Norwegian Geotechnical Institute. I will talk about SENSE, which is basically about measuring ground deformation to understand what's happening in the reservoir. And I have there. So, story of SENSE project, achievements, some dissemination activities, and summarize. This is a very simple cartoon. You can point out here. Yeah. For those who are not familiar with storage part, if you inject CO2 underground, it will expand somehow. These are millimeter, don't be scared. These are millimeter scale movement. And it will show up at the surface to some extent, not 100%, but reduced. So first question in SENSE is how you can detect that uplift, which is at seabed or at surface. So we have used here 6 different case studies to improve methodologies, technology. And we have tested some of those. I will not present all, but some very briefly. Next question is, okay, we measure some deformation at surface. How is it correlated to the pressure? Is it 1 to 1? Is it 1 to 10 or so? So you have pressure in the reservoir, you know, close to the well, but we don't know far away from the well. So uplift, you can measure. How is it correlated to pressure figure? We have inversion techniques. We have, say, modeling tools, machine learning. And we have used these two for correlating these together. And also, we have done a lot of numerical simulation. In the first case, to the left, or here you relate uplift to pressure. Here we do the other way around. So we have a pressure in the reservoir, we assume a pressure, and then we see how much is uplift at this tiny point, which is a very huge area in reality. Very simple structure, and here you have very complex faults and so on. The first slide was work package 1. Now these are work package 2 and 3 in SENSE. Work package 4 is integration of these results. All how we use these measured, say, data, if it is INSAR, if it is fiber optics, and come up with a monitoring workflow. That's work package 4. We have another work package which is coordination. I don't need to talk about that, I think. So this is SENSE in 3 years of work in 3 minutes, 2 minutes. Then I can go a bit into details here. About the first question, how we measure these uplift. I don't have very nice videos like Sevkat showed, but I have a fiber optic cable with me. So what I'm trying to show on this slide, Sorry. There. This is a lab scale, large lab scale, 10 meter long. So we have put down fiber optic with different, lot of different details there, and interrogator or data, say a logger. Then you lift up this with the lifting bags or air bags, lift up the system. Then you measure how sensitive this cable is. These are usually very sensitive if you draw this line along the cable, but it's not very sensitive in this direction if it is millimeter scale. Here we want to show that it is also working if you have this case or this case. You don't see the difference from the right because it is millimeter scale difference. So here we, this is in NGI Norway. So you see some pictures there, different cable arrangement there. Oh, sorry. Sorry. So there we can measure, if you see strain there. So this cable is mainly DSS, strain sensing, not temperature or acoustic. So in this case, we show that it will work with very simple, without any coupling to the bottom or sand. After that, we went to a bit larger scale test. This is in Japan. So you trench a cable, fiber optic cable in a trench. As you see here, this is another arrangement like this one. This is soil layer. You dig under with some and fill with cement. You fiber optic there. You have transducers, a different type of transducers over there. And then this is again small, but you can see frequency change and at different locations. This is something you can correlate to this displacement. My colleagues were very satisfied with the type of testing and the resolution of the cable. About the same question, I'm on question 1 still. Yeah. That's in offshore, not real offshore, but off the coast of Kiel in Germany. So here now we have something 600 meters of fiber optic cable. And a lot of practicalities there. Sometimes you see, yeah, here it's labor intensive, but these are my colleague in the project working with the cable to put down in a trench to go over this zone. And this is a very dynamic, high energy. You have waves, we have so much noise. But in that setting, we were simulating uplift, like if you inject something underground and you lift up the system in 2 millimeter each time. So we lift, these are fiber optics are embedded there. We have pressure sensors and all other instruments. We could demonstrate similar micro and millistrain displacement. Now I move away from the fiber optics. To next question was how these are related to each other. Pressure in the reservoir with displacement at surface. For that one, we started with looking into solution. You have always finite element method, which is time consuming. Then we looked into a solution with mathematics solution called GIRSMA that you can relate pressure to displacement. But it was not very useful in our case. Then we developed a mathematical solution for this. Now we have, this is published, available. You can have different layers in subsurface, different properties. You can even have different compartments in the reservoir and calculate accurately displacement at surface or seabed. How accurate is that? We compared with finite element method. This is a case you see probably these are in shallow wells, so example there. But this is finite element method, and then you have our solution. It's quite similar to finite element, very quick calculation. This figure shows quite similar, say, pattern, but this is completely different approach. We have used machine learning now to go from right to left. So you have surface measurement, and then we estimate based on machine learning pressure in the reservoir. I mentioned simulation and numerical simulation. We have done quite a lot of examples for carbonate, for sandstones, and then you have, here you assume a pressure in the reservoir, and then you come up with displacement at surface, how it is and where you can get maximum uplift. These are synthetic cases, but then we went on and did the same study for Gulf of Mexico, based on data that you have, seismic data, and also material properties that you have. Here is the system reservoir level with a lot of faults. In this, you have underburden reservoir in blue and also overburden and different wells. To the right, you see extra pressure you have in the reservoir and then corresponding uplift. I'll get back to you how we can use this later on. Now, if you have a fault system, how does it affect the uplift? Or if you measure uplift, can you say something about faults? Here is a case with sealing fault, tight. Here is the case with leaking fault or permeable. And the difference in uplift is in a range that we claim you can measure at surface or at sea bottom. In the same line, if you simulate uplift around, for example, this is from Insala, around well, then you can determine which point, which lines will show maximum uplift. Then you can suggest where to put your monitoring system. For example, tilt meter, this is a work showing, again, Insala tilt array. I have some time, right? A few minutes? Yeah. And then at the end, I saw how we can integrate these simulation and measurement together. I have a flyer with me, so in addition to fiber optic cable, so I have some of these here available if you are interested to, at least we have the links and all information about the project metrics here. It simply says a monitoring workflow based on ground deformation, but we see that it should be linked to other, like microseismic events and so on. More specifically, if we talk about ground deformation in a monitoring workflow, then for offshore Norway, for example, we have tested these for Troll field. Now you know Troll is not injection site. It is opposite, so it's going down or it subsides. But mechanism is the same. If you can, based on subsidence, you can estimate pressure depletion, you would be able to do the same pressure increase in an injection site. So we think this will also work for Northern Lights. For offshore US, this is this one. Yeah. This is a picture that shows permeability of those reservoirs. And here you see, I don't see from here, yeah, bulk modulus or stiffness. And based on properties that we have from field, we think based on injection of about 1 million tons per year, you will get around 20, 30 millimeter at uplift at sea bottom. And this is something that we can easily detect with, for example, fiber optics. In offshore, US offshore is not very deep, so it will be a lot of noise and waves and dynamic environment. Therefore, pressure sensors may not be very effective, maybe, but fiber optic will do the work. Onshore, I didn't show any onshore in this presentation, but we have worked quite a lot with Insala data after closure since 2016 up to now. And based on those, can go back a bit. And also UK, we have a site in UK where gas storage is in place. Based on those, we can see that we can estimate what's happening in terms of pressure in the reservoir based on the formation measurement. Dissemination, we have had some journal conference papers and some outreach to industry, public, and regulators. Total about 60 activities. You can see some of them listed here. And we are planning something with Arvid and Guttorm, some dissemination activities later this year, probably in SGT 16, we'll see. And hopefully together we'll succeed, as we had some meetings in the beginning, but we couldn't manage physical meetings or other activities. So that was in short about SENS. I'd like to thank all sponsors that you see here, 6 ACT countries, and we have Equinor and Quad Geometric industry partners, thanks to them. NGI that I'm representing. We have Geomar from Germany, British Geological Survey. We have Wright from Japan with on funding. CUDEN and IGME from Spain. We have IFPEN from France. CSIRO with on funding from Australia. Lawrence Livermore, University of Oslo, UT Austin, and Kigom, South Korea as well with on funding. So in total, 9 countries, all time zones. Amazing for meetings, online meetings. But that's it has been great pleasure to work with all of them. Thank you.
Thank you so much, Bahman. You have used your time exactly, precisely, so there will be no question right now. But anyway, I hope that your results can be shared with the next 2 projects under the storage side. And now we are going into the return, which is the reuse of depleted oil and gas fields. Pierre, please.
Yes, so I'm Pierre Serassi from SINTEF. I'm coordinating this Act 3 project, which is shifting away a bit the focus from storing in aquifers towards depleted oil and gas fields. And it's not a secret that this, the driver for this has been the Netherlands, as you may imagine. So, as mentioned, a new project has started in the beginning of this year. The primary objective is to enable safe and cost-efficient long-term CO2 storage in depleted oil and gas reservoirs. And to do that, we need to understand better handling of cooling and phase changes that may occur when you inject the CO2. So the main motivator here is to enable the industry to cut costs and reduce energy used to compress and heat the CO2 prior to it expanding and cooling into reservoirs. So the total budget is a bit more than 7 million euros. We have 6 participating countries and 18 project partners. So we have Norway coordinating, we have the Netherlands, UK, Germany, Canada through its Alberta province, and Italy in parentheses because they are kind of, it's an industry partner joining through their UK office, but nonetheless the researchers are based in Italy. So that's some numbers. Here you see the partners, and we are really glad to combine universities with Utrecht here in the Netherlands, the Freiberg Academy in Germany, and the University of Cambridge in the UK. We have the usual suspects of the research institutes. You've heard SINTEF mentioned a lot. Then TNO also has been mentioned this morning, and we're glad to continue this fruitful collaboration that we've had in both Act 1 and Act 2 projects. We have now they're called Carbon Management Canada from Alberta with their field lab. And we're really happy to have all these industry participants. From Norway, we have, again, two usual suspects with Equinor and Lundin. From the Netherlands, we have quite a few. We have Shell, EBN, Neptune, no more. And then from Germany, Wintershall. From the UK, the Net Zero Technology Center, not really industry, but they were called the Oil and Gas Technology Center, now switching towards net zero. We have Chrysaor, who now are called Harbour Energy, and we have BP. And from Italy/UK, Eni. And from Canada, we have two, one hydrogen company, Spectrum, and we have also a very small company in Calgary, which are kind of working together with CMC. So, as I was saying, most pilots, demonstrations, and large-scale CO2 storage operations target aquifers. This is also the case for the big one in Norway, the Northern Lights. And it is in the process of changing with, for example, what you've heard about Porthos and the gas fields offshore or near onshore Netherlands. What are the advantages? Working with depleted reservoir is that I kind of naively would think that you have a very large capacity because you've taken out all the gas or oil that was there, so you have some empty pore rooms that you can fill. But on the other hand, also from the risk aspect, you're going from a low pressure, as we heard with Bachmann before. Here you will be pumping in CO2, but you will only bring the pressure to maybe close to what it was originally in geological time. So you're not kind of stressing too much the reservoir and the overburden. The drawbacks is that we know that the depletion process, so the reduction of the pressure when we were producing the oil and gas, is not a uniform process in terms of the stresses, the forces on the rocks. So even though the fluid pressure is uniformly kind of reduced, you have, it's also alluded in the last presentation, you have these stress arching or stress concentration effects, which mean that you have to be careful to see how you will reverse this process. And as mentioned in the beginning, this Joule-Thomson effect of the expanding CO2 could lead to very significant temperature changes. So the advantage of injecting the CO2 without perturbing it in any ways could be risky. As now you would maybe switch from supercritical to gas phase to avoid some of these effects, but the industry is really pushing forward to try to see how much we can push the envelope without putting too much effort into it and energy. So the project impact, it has only started, so we're always very optimistic at the start, but I think that with so many industry partners, we better deliver. If not, they will not work with us anymore. As I said, we want to enable cold CO2 injection into depleted reservoir so that we don't expand too much energy. And what we want the project to do is to offer operators recommendations on whatever they can control of the parameters, be it operational or design architecture. And this will reduce the costs, but of course we have to always make sure that we increase the safety, we don't compromise on that. And what we want to do is have a very strong communication focus. I think that yesterday I was kind of lurking in the shadows of the internet, but the debate we had was very, very interesting. And there was a lot of mentioning of the oil and gas business. So everybody talks about greenwashing, so if we don't have a strong communication, then we've lost the battle before we even begun. So I think that when we are talking especially offshore storage, everybody is kind of reluctant with onshore storage, at least for the moment. There we really need the industry who has the technology, who has the experience, and I personally don't see how we can work without the oil and gas industry, and how we can introduce new partners while we're talking about large-scale storage now, not in 50 years. Also in 50 years, but at least now. So the key targets of the project is to, by including these old reservoirs, not only aquifers, we want to increase the available storage space, since we need gigatons. And we want to increase the confidence that this is possible, and also reduce costs. And that's the whole thing about enabling cold injection. Next one, yes. So we have we only barely started, but we have some initial results. The work package 2, I'm only citing 3 work packages where we've had a lot of meetings and a lot of enthusiasm. And it's good that we are going over to in-person meetings, but at the same time, as Bahman was saying, we have Canada. It's a bit less, we don't have Australia, so that's solved. But it's difficult. We have so many partners that many of them are still, we need these hybrid meetings. But luckily, we've had a lot of enthusiasm and many participants in meetings. So work package 2, you'll see in a minute. It deals with looking at the flow models from coupling the well where you're injecting the CO2 and the near well area, the reservoir. And there we've had some calculations made by principally by EBN here in the Netherlands, and some of them by University of Cambridge, looking at what are the windows of operation where you can avoid, on one hand, freezing of the well fluids, and on the other hand, formation of CO2 hydrates in the near well zone. In work package 2, that's more of the lab work, again, looking now at the near well, so mostly rock mechanics and simulations. We're going actually next week to this charming location on the east coast of the UK to steal some cliff rocks, some shales, hoping that we don't cause the whole town to subside. Which is, it's a way to get large or relatively large volumes of rocks without getting them from a well where you're reduced by the size of the well. And in Germany, they already started some reference tests looking exactly at what are the conditions inside the pore rooms of the rocks for formation of these CO2 hydrates. Work package 5 is interesting because it is led by TNO, but involves a lot of the industry partners, because here we're looking at field cases that we're going to learn from. And here it's to not waste energy in our experimental work, to look at conditions which are not interesting or not realistic for the field. And then we will, based on this interaction between the researchers and the industry operating on the field, we will devise also a numerical synthetic model that everybody can work with. Yeah, I think I missed a slide, but that's okay. There was just a diagram of the work packages, because it's very interesting. Initially, when you look at the competence and the people working in ACT, it would seem that it's a strange gathering of different disciplines. But actually, we're really looking at the well, at the border between the well and the reservoir, and the reservoir at large scale, and also tying it to the field conditions. So here you have the website if you want some more information. It's already live.
Thanks a lot, Pierre. Not only have you reused the depleted oil and gas fields, I also see that you reused the colors from ACT, which you are welcome to do. It's great. Very promising results. And personally, I really acknowledge the focus you have on communication. This is crucial. Really, really crucial. So look forward to see more collaboration and interaction with the other projects also in that sense. Thank you so much. I learned that reservoirs can have stress. I don't know if you are stressed here you are right now, but definitely we will hear more about the stress history and the reservoir pressure from the SHARP project. So please, Elin, take the stage.
Nice to be here and see all of you. It's a project that has been developed and through online meetings, so it's nice to finally meet some of the people involved in the project. So yeah, my name is Elin Skurtvedt. I'm from NGI and coordinating this project. So SHARP storage, and yes, it's about stress. We have a really nice consortium in this project with partners from Norway, UK, Denmark, Netherlands, and India. And it's 4 of the countries are gathered around the North Sea. So it's about storage in the North Sea and how can we learn from each other and help each other to understand the stress conditions in the North Sea and utilize that for both monitoring and reduce the risk. And then we have India as a partner, and they are in the project mainly to learn and hopefully kickstart also CCS in India. So the main aim is to increase the accuracy of subsurface storage containment risk management, and we will do that by improving and integrating subsurface stress models, rock mechanical failure, and the seismicity observations. So I'll go through the background for the project, and of course it's to reach the climate goals. There needs to be gigaton per year scale CO2 injection. And when doing that, it's important to understand the stress system in the subsurface where you are injecting. And when talking to the industry and those operating injection fields, there is some uncertainty related to the geomechanical response of CO2 injection. And that was kind of the background for this project, but also that there is potential to improve risk assessment and by integrating data and knowledge from various fields and from various parts of the North Sea. And especially we'll look into the rock failure models and seismicity data to provide a better link between what is done in the laboratory and what's done or what you can learn from earthquake analysis and how you can utilize that also for monitoring. So the objective, these are kind of grouped also, so they represent the different work packages. So first we have basin and site scale geomechanical models for the North Sea. And in the North Sea there is different challenges. There is salt diapirs, domes that create stress, a certain stress field. There is a lot of faultings closer to the Norwegian side, and there is also observations that there is some kind of changes in the trends for the stresses with depths. And these are the things that we'll look into in more detail. It's also kind of earthquake database from the various recordings in different countries around the North Sea, and there is a need to integrate these catalogs for earthquake and produce better stress maps and also understand the the slip and modes of failure in the ground from earthquakes. And then the characterization of the formation and failure, flow, and the seismic properties. Also, what can we do in the lab? So there will also be lab programs in the project. So, and that was the 3 basic objectives related to very kind of basic scientific topics. And then the more applied part of the project is to develop cost-efficient strategies for monitoring induced seismicity. It's concept of right time, right place. So can we be better at monitoring the correct areas where we know the stresses will be high and will be most prone to failure. And that will take part and also included in the risk assessment, because you can reduce the risk if you can have good targeted monitoring of your reservoir. And of course, we also have a last focus on communicate both the technology development and the containment risk to both the industry and the regulators, so that everyone can benefit from what we can learn in this project and what we will develop. So the project is it's also focused on case studies to demonstrate the value of what we are doing. So in the UK, it's the Bunter Sandstone, a Greater Bunter Sandstone area. So Endurance is Bunter Sandstone. There is also other areas, and these are the areas with salt tectonics and special stress field related to that. In Norway, it's the Horda platform area with Aurora and Smeaheia. It's quite a mature area, and there is new wells recently drilled in this area, so there is a lot of data available for integration. There is also a nice seismicity network in that area. Then we have Denmark with Lisa and Nini field. So Nini is a depleted gas field. Lisa is a saline aquifer structure. Denmark is quite recently increased the interest for CO2 storage, and they are interested in learning from the other projects, and also have a focus on the seismic hazard and monitoring. And then in the Netherlands, it's Armis project, and especially risk assessment related to depleted fields. That is a special topic of interest. Whereas in India, there has not been much related to CO2 storage so far. So it's about developing new project and gain interest from CCS, both in the industry, researchers, and the population in general in India. So, of course, we hope that this project can make an impact, that we can facilitate emergence of CCS as a response to the demand for sustainable storage in Europe and also globally. We hope that we can demonstrate technology that can ensure safe and cost-efficient operation of offshore geological storage location. We want to contribute with knowledge framework and databases for relevant for CO2 storage, maturation, and regulations, and that the work we do can actually be used in both these projects that are going on right now, but also future projects in the North Sea. And also have a scientific base for the risk communication to public and the regulators. So this is the work package structure. So we have 3 work packages: scientific topics of stress history, seismicity, rock mechanics, investigation stress-strain relationships. And it's not like a straightforward workflow. It's a kind of interaction and integration of these 3 areas. And then these 3 areas will again be integrated with monitoring and risk quantification methods to create sharper models, so that we can do monitoring at the right time, right place. And then there is a management structure for the project. So it's a great team that is involved here. All the work packages are led by people from different partners. And I know that we have from Work Package 1, Rockfield, Daniel Roberts is here. Work Package 3, led by Shell, Kees Hinrichs, he's also here. And Åke from TU Delft is coordinating the Dutch part of the project. So unfortunately, I have to leave after my presentation, but there is people from Sharp here that you can talk to if you have more questions. And a little bit about our timeline. So we started in the end of 2021, kicked off the project, and we do have regular consortium meetings twice a year. We're gonna finalize the project within the end of 2024. So this is an Act 3 project. And we also have some workshops and seminars planned. We have had some internal presentations of all the case studies, trying to update each other on the status for the different case studies. And then we will have a risk workshop in Copenhagen in September. That's kind of what is planned for now, but we will also try to aim for more detailed presentations on the North Sea stress system, monitoring optimization, and risk quantification before the end of the project. So the work has just started, but we have actually had very nice progress in this first 6 months of the project. This is North Sea earthquake catalogs, focusing on the North Sea and kind of combining catalogs from all the different countries. And there is a lot of work now to clean up this database and actually find out what is the relevant data here and how can that be used further in the different projects or tasks in the project. We have also other stress data that we are working with. So these are measurements in the wells, and there has been release of new data from the industry, and it's also about understanding and analyzing for various trends in the stress measurements within the North Sea. And then one of the things about this project is to also include the stress in the overburden, the glacial contribution. There has been glaciations of large parts of the North Sea, and we can clearly see on the stress trends that is contributing. So this is a nice mapping of the very shallow surface seafloor, and that shows examples of folding and thrusting due to the glaciations. And there is definitely differences between the UK side and the Norwegian side when it comes to how what the glaciations has done to the seafloor or to the sediments. So this is something we will incorporate into the new models. So the two first deliverables are in place. So one is the guidelines for uncertainty quantification of rock mechanical properties. And this is part of the work package 5 on risk assessment. So the methodology has been reported. And there is also a methodology for the quantitative modeling of CO2 storage containment risk. So both these deliverables, reports, will be available on the website very shortly. I don't think I managed to get them uploaded before the meeting, but that will be done. So if you want to know more about Sharp, you can have a look at the website. You can follow us on Twitter. There is also the risk workshop coming up with GEOS in September as an in-person event. And we have plans for a poster on the GT16 conference, so you can come and talk to us there and hear more about our progress. So then it's just acknowledging the funding and all the partners that are doing a great job contributing to this project. Thank you.
Thank you, Ellen. I know you are in a hurry because you need to catch the plane and try to avoid the long queues at Schiphol. But thanks a lot. You have mentioned your colleagues here in the audience, so if they can just stand up so we can see them. There they are.
Yeah.
Yeah. So if someone want to know more about stress,
Yeah.
in the reservoirs,
Yeah.
contact them. Thank you very much. Great success with this project also. I'm really impressed what all these projects now have achieved, also those starting late last year. It's really good. So now we will have a new break. Only 10 minutes this time. Be sharp and be back in time.
Start on
Yes.
sharp on time.
Yes, sharp on time.